Hi there, I'm Jayal Sahgal from the batch of 1967. I'm delighted to be part of our alumni reunion this evening. And I'm also very delighted to be part of our 50th anniversary of to be the 50th anniversary of our graduating class. It sounds like a long time, 50 years, man, but it feels like as if it was yesterday. And we have fond memories of Naseem Bagh, and we do plan to reminiscence tomorrow too, but don't worry about it. I'll have my chances tomorrow, right? I'm just representing our class of 67, but our classmates and a lot of alumni have stellar achievements in their own professions, and they are leaders in their own communities. And I think we should give a big hand to all the classmates and alumni that are. Graduated from the University of Miami. I'm going to hit on 3 or 4 items because I got only 10 minutes. And jet engines are common, but they are also very complicated. And they extend the limits of our turbo machinery, structures, controls, performance operability, and it stretches the limits of material sciences. And that's a great, great field and a dream for, in my opinion, for a mechanical engineer to work on fighter jet engines. Briefly, to give you my background, I went to University of Miami in 1969, graduated in 71. And I had a couple of assignments, and one of the assignments was on the space shuttle program. I was part of the team that designed the mechanical arm. It was funded by National Research Council in Canada, and I was part of the team that was working on an end effector. If you look at the morphology of the remote manipulator system, it is just like a human being. It has a shoulder joint, it has an elbow joint, it has a wrist joint, and the end effector which grapples and deploys the payload. I'm sure all of you have seen a lot of pictures of space shuttle and primarily the payload that is being deployed and retrieved in space. So after that assignment, I was recruited by GE in 1980, and I came to work basically as an individual contributor working on design of some sensors, primarily a fan speed sensor and inlet temperature sensor, because both speed and pressure are very critical in the turbo machinery. I grew through the ranks of GE and eventually became a manager of engineering, and I headed up an F-110-100 team. That engine is used for F-15 and F-16 fighters. And I'm sure you've been reading in the newspaper lately that the Secretary Matt is here and trying to sell some more F-16 fighters, and primarily trying to set up a manufacturing facility that Lockheed wants to do it. And for my young friends who are watching this thing, keep an eye on a lot of openings if Lockheed Martin were to open a manufacturing facility in India. And that's going to give you a lifetime experience of working in the latest state-of-the-art technology. And it will be very, very fulfilling. I'm going to hit on some of the overview of military engines, talk about the F-110 engine, and then I'm going to talk about the service life engine program. As you know, GE has been there. You have Rolls-Royce, you have Pratt, you have GE. I'm just focusing my attention on the military engines that are made by General Electric Company. GE has been in this business for a long time, and some of us who have been mature and old enough to recognize J-79 engine was deployed in 1955, and that engine is powering F-4 Phantom in Israel. And it shows you that GE has a demonstrated ability to execute and provide innovative technologies in the field of military engines. Briefly, there are a lot of models that GE makes. GE make engines for the F-1, for the F-16, F-15, U-2, B-2, B-1, F-22, Joint Strike Fighter. So there are so many different engines. And right now, GE is working on the 6th generation fighter. 5th generation fighter is the F-35 weapon system. That's called the Joint Strike Fighter. And you might have seen some of the pictures that our Air Force deployed an F-35 in South Korea just to show what that can do. Right? Now the 6th generation fighter engine that is still in the works uses an adaptive cycle. And that adaptive cycle is basically providing 3 streams of air. Typically in a turbine machine, you have the fan and the Now, on the F-16, it uses this F-110-100 engine, and I know I have only 10 minutes, and basically this engine was developed in 1986. Initially, Pratt & Whitney F-100 engine was powering our F-16 fighter Falcons, but they had a whole bunch of reliability issues. They have stalls. The pilot will have a non-recoverable stall, and the engine won't restart, and resulting in a Class A or basically an in-flight shutdown, and resulting in the loss of the aircraft. That necessitated the Air Force to initiate a competitive on the F-110 on the F-16 program. So they funded GE for an alternate engine to F-100 for the Pratt engine, and we came up with an engine that is physically and functionally interchangeable, but is a lot more reliable. It provides more power, and there's no more stalls, and the pilot can go around and jockey it around. And typically we go and do the mission analysis. We want to go and see how the pilots are flying it. For the cumulative cycle, it basically measures the damage on the fracture critical parts and the durability parts. Now the fracture critical parts are the ones, if you have a crack and it propagates to failure, it's going to result in a Class A, that means the loss of the aircraft. So moving along, that basically drove the need for an innovation on the F-110-100 program. And I like this program. And it has created about $1 billion for GE, and we have provided several $1 billion of cost effectiveness for the Air Force because we reduced the number of unscheduled shop visits. So we have increased the time on wing. And there are a lot of areas in this area, in the SLEP program, that were based on the experience, how do we improve the life of the compressor. In the past, we used to do a 2D compressor, but the 2D compressor causes a lot of instability in the airflow. And going to a 3D compressor, we were able to make it a laminar flow, improve the efficiency of the compressor. The same thing we did with the combustor. We made a lot of changes in the combustor area to increase its life. And on the HPT turbine blade, anytime a jet engine comes back, you will see oxidation, you will see erosion, you will see the tip curling on the high pressure turbine blade. And that was driving significant amount of unscheduled removals. Unscheduled is not supposed to be brought out of the aircraft because you have a certain schedule in it. So we came up with a kit that was used to upgrade the whole F-110 fleet. And as I mentioned about it, was a big business boom for GE and also for the Air Force. And this SLAB program is now being used on different derivatives of the F-110, like the F-110-129, the -132. These are all different thrust levels for different applications. Quickly, I'll talk about the 6th generation fighter jet engine. And there's a great team that is working on it, the best of the best minds in the world that are working on this adaptive cycle. And basically, for our friends, our students at RAC campus, keep an eye on, especially even for the faculty members, to start addressing some of the new technologies like the 3D, additive manufacturing, ceramic matrix composites. And these are the things, as Azur said, you don't have to reinvent. The innovation is there. How do you adapt? the ceramics for rotating parts, how do you adapt the existing technology in the 3D manufacturing. Just to give you an example, a turbine blade will take about 3 months to make it. Now you can do it in 3 weeks. So it is a big cost-effective way of making parts. And by the way, for our ladies who are sitting here, very soon you're going to have a 3D technology where you can go and order your shoes or your dress without having to go to a dressing room or checking it out. Yeah, right. And this engine gonna be rated at 45,000 pounds, so it gives you some additional thrust and also allows you for a lot more action. It's a stealth application, provided the Air Force will go along with that. So basically what I'm saying is, working in a corporation, especially at a GE, is a team approach. You win as a team, you lose as a team. As a leader, you have to go and get the work from so many different experts. You have tons of experts, centers of excellence, and how do you provide the leadership by influence? They don't report to you, but you have to go and get them to work together and converge and work in a team. Our former GE CEO used to give us this 9 and 10 points. I won't go into details on any of those points. It's especially for our young engineers to understand. I'll simply say, please understand breadth, depth, and context. If somebody gives you an assignment when you're in the real life, try to make sure you understand the context of that assignment, and then use your breadth and depth. Depth comes with, the fundamentals and the experience and the education, and the breadth comes from your interpersonal skills. How do you get the best out of your teammates? So these are 9 or 10 points. I'm sure Sarabjit will touch on some of those items in his presentation. Lastly, I'm proud to be an REC alumni. The hard work and the culture and the values that were basically given to us by our faculty members, I am highly grateful to all of them. Like we talked about Dr. Zader, Dr. Qazi Ashwaq Ahmed, there are a whole bunch of excellent faculty members, and we are, and I am indebted to their teachings, education, and helping us during my 5 years. Thank you.